Okay, in this video we're going to talk about periodic trends that we see in the periodic table, patterns, and in total there are, depending on what website you look at, between 6 and 7 trends in the periodic table. But I am only going to have you guys know 3 of them. Okay, so the first trend that I want you to know is atomic radii. Okay, and the radius of an atom is just like the radius that you know about in math, and it's the distance from the nucleus to the outer ring of electrons. And we see a periodic table here that shows starting with hydrogen and going down. As we increase the number of valence shells, then the radius of the atom gets larger. Okay, so here we see just the group number 1, hydrogen at the top. It has 1 electron shell. Then we go down to lithium with 2, sodium with 3, potassium with 4, rubidium, and so forth. And you see, as we add electron shells, the radius gets larger and larger. It shows hydrogen. Hydrogen has the 1 electron shell, and so you see the radius this big, as opposed to sodium, who has the 3 electron shells, and the radius is much larger. Okay, now we're going across the periodic table, starting with the 3rd period, sodium, then magnesium, then aluminum, and all the way across the 3rd period. Now, all of these have 3 valence shells. So what's the difference? Well, sodium has 1 valence electron, magnesium has 2, aluminum 3 on a cross, and you add 1 as you go. Well, what does that mean? Well, think about the protons. What's in a proton? What's in the nucleus? Positive protons. The protons are positive. And these positive charges of the nucleus are pulling on the negative charge of the electrons. So if we have just 1 electron here that these protons are pulling on, it really doesn't pull in the rings, as opposed to argon, who has 8 electrons in the valence shell. These protons can reach out and each grab on to one of the 8 electrons, and it pulls those electrons in, so it has more electrons to pull. So that's what causes the radius to get smaller as we add electrons from the left of the periodic table to the right. And here you see these arrows indicating the pull towards the center of the atom. And a good way to remember this electron radius is to think about the 2 words big bottom, large left. So as we go to the bottom of the periodic table, the radius is getting bigger, and as we go from right to left on the periodic table, the radius is also getting bigger. So the biggest radius is going to be here, big bottom, large left. The second trend that I want you to know is called electronegativity, and the definition of electronegativity is the ability of an atom to attract electrons. And we see here an example of fluorine and chlorine. And it's the ability of this atom to attract electrons. So the positive nucleus attracting electrons. If we look at both of these, they both have 7 valence electrons. So if they had just 1 more, then they would have a full valence shell. So both of these want just one. Well, which one has the ability to attract the electron? Well, we can see that the distance in fluorine is less than the distance in chlorine. So the positive pull of the nucleus is going to be felt more in the shorter radius. So fluorine would be the one that's the most electron negative, with chlorine being less and bromine being even less. The third one that I want you to know about is ionization energy. And the definition of this is the energy required to remove an electron from an atom. And this depends on how close to the magic number an atom is, that magic number being 8 in the valence shell. And also I want to introduce a vocabulary word, ion. An ion is an atom with more or less electrons than protons. So we've been talking up to now about elements having the same number of protons and electrons, but sometimes the electrons get removed, and when they do, the proton number doesn't change, it stays the same. So if we lose a negative electron, then the net charge of that atom is going to be a +1. So how easily does an atom give up its electrons? Well, if we look at sodium here, sodium has 1 electron in its valence shell, and it wants 8. But let's look at the shell that's right underneath that. It already has 8. So if sodium can just get rid of this 1 electron, then it will look like a noble gas with 8 electrons in the outer shell being filled. As opposed to chlorine, chlorine has 7 electrons in its outer shell. So if it could just get 1 more electron, then it would have a full valence shell and it would be happy. So the ionization energy of sodium is very low. It does not take very much energy at all to strip that electron off of sodium. In fact, sodium wants to give the electron away. However, in chlorine, with 7 valence electrons, it's going to take a lot of energy to try to strip one of these off, because chlorine is searching for just 1 electron to be full. So if sodium were to give away its electron, chlorine would have a full valence shell. If we get rid of this shell, then sodium now has a full outer valence shell. So they're both happy. So what does that cost sodium? Well, sodium lost a negative charge, so it now becomes positive. Chlorine, the protons in the nucleus didn't change number, but it gained an electron, a negative electron, so its overall charge now is negative. So now we have a sodium ion and a chlorine ion. And here are the trends for electronegativity, atomic radius, and ionization energy on the periodic table. Now the way we write ions is by using brackets. So if sodium is now an ion, we put a bracket around it and put the positive charge out here. And the same with chlorine. Chlorine is now an ion, so we put a bracket around it with a negative charge out here. Now, what do we know about positive charges and negative charges? If you said they attract, you're absolutely right. So sodium ion is now attracted to the chlorine ion, and they bond together to form sodium chloride, which is what we call table salt.